Evening. I would like to thank you for being present in my proceeding presentation. My name is Gustikit Faiksha. I am from Mechanical Engineering Department of 11 Maret University. And what I am about to present is towards bullets, residual velocity, and plates stress contour under ballistic impact, an idealization of ship casualties under piracy. This presentation will be divided into 5 sections. The first one is introduction. Second is literature review. Third is numerical modeling. Fourth is result and discussion. Fifth is conclusion. For the start, in this world, maritime transport accounts for over 80% of the world trade volume and is the backbone of global economy. As of 2016, more than 49,000 merchant ships with almost 1.8 billion deadweight tons were operating, where of these oil tankers, bulk carriers, and container ships took up to 28%, 43%, and 13% respectively. If we look at the chart to the right, in 1970 until 2023, grounding, fire, and collision are the most cause of oil tanker spills. And ballistic impacts are impact where the projectile is relatively small and have high velocity. Thus, it could cause an lesion and cause fire or explosion. And in transporting oil, there are dangerous events that could occur while transporting. And one of the most common threats are piracy, modern piracy. They potentially carry firearms that could harm the ship and the crew. Modern day pirates uses speedboats to reach their targeted ship, and they usually carry firearms such as rifles, pistols, even rocket-propelled grenade. Those are used to threaten the ship's crew to hand over anything valuable to the pirates itself. Oil tanker ships should be in high risk due to the possible chances of shootings between ship's security and the pirates itself. Bullets from pistols, rifles are considered as ballistic projectiles because of the high velocity and the small size that it has. The high kinetic and thermal energy of ballistics can puncture, dent, melt, burn, and knock down structures and their associated systems. The ship and the environment will be in great danger if the bullets comes in contact with flammable substances within the ship, such as oil or gases being in the transport. The risk of oil spill effects are the sea environmental pollution, worldwide economy, and the safety of ship's crew. One of the tragedies happened is the Deepwater Horizon accident, where tens of thousands of sea creatures died because of the oil spill. And our objective in this paper is using LS-DYNA numerical approach to investigate the factors that affects the energy absorption of targets and velocity reduction of projectiles at impact with the bunker walls. Previous researches had been done about projectiles launching into target plates. The first one is from Rosenberg and others about plate perforation with the target of aluminum plate. They focus on the effects of entrance phase on the resisting stress, which a short projectile experiences during its penetration to semi-infinite target. Second one is Goda and others about armor with the target plate of woven composite panel, focusing about ballistic limit velocity of the target. The third one is the one used for this paper's benchmarking from Alwan and others about defensive plate with the target of aluminum and magnesium panel, focusing on the energy absorption of layered target plates with ballistic projectile. This is the scheme of experimental method taken from Alwan and others paper. It is served as the main reference of the simulation on this paper. The pressure chamber will be filled with pressurized air by the compressor, and by the time comes, the projectile will be launched by those pressurized air moving in high velocity into the targeted plate and being caught by the projectile catcher. The function of the camera is to get the value of the projectile's residual velocity after impact. And the relationship between the nose vector of projectile and impact velocity is served in the equation below. For the material used in this simulation is aluminum 1100 H12, the same material used at previous researches to get benchmarking results. The numerical model is a 315 millimeters diameter aluminum plate with the thickness of 1 millimeters, held in place with 9 holes that acts as plate holder in the experimental method. These 9 holes are set as fixed constraints in the simulation. Then the meshing strategy used is dividing the plate into 3 sizes distributed evenly to reduce computing load while having accurate results. The contact zone used the size mesh targeted, and the non-contact zone uses 2 times of the mesh inward of the plate. For example, if the contact zone is set to 1 millimeters, then the first non-contact zone is 2 millimeters and the most outer zone is 4 millimeters. The conditions set on the projectile are to act as a rigid material using EN24 steel with initial velocity of 107.7 meters per second, heading towards minus y direction or into the middle of the plate to the contact zone. Then the plate is defined as power law plasticity material using aluminum 1100 H12. The benchmarking results shows the difference of each analysis, comparing experimental analysis, Abacus numerical analysis, and LS-DYNA numerical analysis. It is noted that experimental result and Abacus result is taken from the paper of Alwan and others. And the LS-DYNA is from this simulation. It is shown in 3 different initial velocity taken from the experimental analysis with 107.7 meters per second, 102.7 meters per second, and 95.4 meters per second. The most right side is the difference percentage between each numerical analysis with the experimental analysis. For Abacus is 8%, 7%, and 6%, and LS-DYNA is 1%, 2%, and 23%. The deformation compared is in this screen is LS-DYNA numerical result at the left side and experimental result at the right side. The deformation shape after the impact are relatively similar. Here are the progressive deformation from LS-DYNA simulation from 0 milliseconds to 0.8 milliseconds with the increment of 0.2 shown in the lowest, middle, and the highest mesh size from 0.6 millimeters, 1 millimeters, and 1.5 millimeters mesh. The contour shown in this comparison is the von Mises stress contour. As the time went by, there are differences on the plate deformation in comparing the 3 major sizes. If we look at the post-impact images, the shape of deformation and stress distributions are the highlight of this comparison. Smaller mesh tends to give more precise look, while the bigger mesh will give rougher deformation. This graph represents the residual velocity and energy absorption between mesh sizes simulated. Residual velocity graph is moving downwards as the mesh use is bigger, is the right one, and the left one is energy absorbed. It goes higher as the mesh size is bigger. Thus, the conclusion of this paper, our first one is The distribution of von Mises stress is significantly affected by the mesh applied to the structure, regardless of the material type. Second, larger meshes tend to produce lower residual velocities than smaller ones. The mesh size affects stress distribution, and smaller meshes give more accurate results. And my recommendation for further work is that this study has limitations as it does not account for additional impact conditions, such as deformable projectiles or other realistic scenarios, which could provide a more true evaluation of structural and material behavior. I believe I have reached the end of this presentation. Thank you for the time and attention given to me for this presentation. I hope what I have presented will be useful in the future.